Welcome back. We've been on a journey from classical symmetries, classical conformal symmetries, what are they, to the implementation of these symmetries in a quantum setting. So what do the constraints of conformal symmetry look like on a quantum theory? And at least in the context of quantum field theory in 1+1 dimensions and in d+1 dimensions, in 2+0, 1+1, and indeed d+1, we have constraints on the forms of the correlation function. Okay, that was the content of the previous lecture. We had a look at the correlation functions of a putative theory in 2+1, 1+1, or d+1 dimensions. And we said, well, if this theory is to be invariant under the conformal group, what is the possible allowed forms for the correlation functions? And so it's sort of the generic result one finds is that the two-point function is inverse polynomially decaying with separation. That's the generic sort of outcome of this investigation. We also looked at higher order correlation functions, and we also derived a bunch of results on those as well. So that's the sort of short and long of it all. If you have a quantum field theory that's invariant under the conformal group, then that conformal symmetry manifests itself on the correlation functions in this way that we discovered, and that's all the observables there are to a local quantum field theory, so we're in a sense sort of determined everything up to a bunch of horrible constants. That was the content of the previous lecture, but this was all sort of predicated on us having a quantum field theory to begin with that was conformally invariant. So if you have one, then these correlation functions must behave in these particular ways that we saw. But we don't yet have one, right? It might be that if you try and look for a conformal field theory in these space-times, you don't actually find one. There does not exist a non-trivial conformal field theory. We haven't exactly excluded that possibility yet. And so what we're going to do is try and construct one, or at least I'm going to give you a physicist heuristic approach for how to construct conformal field theories, and plenty of them. There do indeed exist conformal field theories that are proven to exist at the level of mathematical rigor. We'll certainly look at one, namely the free boson. And there's a bunch of other conformal field theories which we understand to exist, and most of them at a level of mathematical rigor now. But I'm not going to do the rigorous approach, of which I mentioned briefly in previous lectures. There are three. I would prefer instead to work with the physicist approach, which is much more immediate, gives the results in a very physically clear and transparent way, and you gain a lot more intuition, I would argue, from the physicist approach because it's so simple and you see how it can be implemented. But in order to accept the physicist approach, you have to use the path integral. So this is the price one usually pays, right? Okay, the topic of building quantum conformal field theories via this physicist path integral approach typically falls under the title of the radial quantization. So I put the scare quotes around quantization, as I always do. Quantization, it's not any kind of functor, right? It's just a guess. It's just a inspired guess. So whenever you hear the word quantization, Don't think that I'm telling you a mathematically rigorous procedure. I'm just showing you how one might guess things. And we're going to try and build a quantum theory in 2 + 0 dimensions, a quantum field theory in 2 + 0 dimensions, which exhibits conformal symmetry. I'll give you, roughly speaking, a recipe for how to do that. So a conformal field theory is a quantum field theory, so we need a quantum field. So what do we need, or what is a quantum field theory when you strip away all this additional stuff? A quantum field theory, well, we can associate to it a Hilbert space. That's the kinematical space for the field theory. It's just presumably a separable infinite dimensional Hilbert space. We're going to want a vacuum vector. There's some special vector in the theory corresponding to the vacuum, which should correspond to be a state of lowest energy. I won't go into those. I'm going to stress rather this last point for today, which is that observables, we want a bunch of observables, right? A quantum theory, just a Hilbert space alone is a kinematical space, but until you say what the observables are, this quantum theory has no dynamics, and that's what we need to specify, and that's what differentiates all these isomorphic Hilbert spaces. Right? So if you have a separable infinite dimensional Hilbert space, then you know, then it's just isomorphic to L2 of R. What's the difference between every quantum theory with a separable infinite dimensional Hilbert space? Well, if you didn't have any observables, or you didn't say anything about the observables, actually not, right? There's no difference. All these theories would be the same. They'd be isomorphic. What differentiates quantum theories is what subset of observables you say you can measure and what ones you can't measure. That's where things get interesting, right? So you focus on subsets of, I'm not going to write bounded operators here, I'm going to write linear operators. And the choice of subset here is what gives the quantum field theory what distinguishes one quantum theory from another. So up to this moment, like L2 of R, that's the Hilbert space of, say, the hydrogen atom. And that's somehow the same Hilbert space as the bosonic quantum field at the level of Hilbert spaces. That's actually correct. What differentiates the hydrogen atom from the bosonic quantum field is the subset of observables you allow yourself to measure. And we've got to label them. In a quantum field theory, we're going to label them. Well, they're going to have hats. This is the moment in a conformal field theory presentation where the potential for confusion is at its highest, because we're going to talk about classical fields and quantum fields almost interchangeably for the next couple of hours, because we're using the path integral. And there's implementations of symmetries on the classical side, on the quantum side, and it's very, very quickly one can fall into category errors and get confused. So I'll try and remember to put the hats on the things whenever, ever it's quantum. So we have a bunch of observables. What are we going to assume about them? Well, we're going to assume that they're labeled by positions. So our observables somehow locally sense the quantum field at a space-time location, say x and y. So, and this vector xy is an element of R2. So there's plenty more requirements to be called a quantum field theory, but here's three that are sort of the very bare basics. Every quantum field theory is going to want to be able to understand these three things. These are the observables we care about. They're labeled by locations in Euclidean space-time, x, y. X and y are real numbers. So that doesn't, want to be clear here, right? This is just a bunch of presumably, well, they're not self-adjoint operators, they're distribution valued objects, but you can think of them as just Hermitian operators, just there's not a particular harm in doing so. It's a bunch of observables labeled by X and Y. We're not going to have observables labeled by strings. We're not going to have observables labeled by regions. We're going to have observables labeled by X and Y. And that corresponds to an experiment which senses the field at exactly the space-time location X, Y. Now there's another aspect that one should stress. And this is also, I find, quite confusingly presented in conformal field theory texts. We look at 2 plus 0 dimensions. Largely, we will today. Although I will, some comments I can make on in more generality. What does this even mean, right? What does this mean quantumly? Well, space and time are on the same footing here. And there's a lot of ways to get confused about that statement, but the cleanest way to think about it is so what this should mean is that our quantum theory yields a projective unitary representation of the conformal group of R2O. That's what I taught you to understand this means. However, often people utilize a very nice fact to turn this around, and you will see this kind of presentation I'm about to give in a second. And I don't prefer that directly. I prefer thinking about it this way and noticing the following as a useful tool to build these representations. So what I'm talking about is imaginary time. So you've probably heard this phrase, imaginary time. And there's no way of avoiding it. We will have actually to exploit this construction. It's not uncommon to hear people speak of a quantum field theory in 2 plus 0 dimensions as the imaginary time version of a quantum field theory in 1 plus 1 dimensions. Probably heard this, you've probably seen that. So if you let, say, that coordinate there, x, you say, oh, x is just I times some other coordinate t, and we leave, say, the y alone. Actually, I suppose for this, it's probably nicer to change this. It doesn't matter, right? In R2 with conformal group, that's rotationally invariant, so it doesn't matter which one you call space and time. But if you just say y is it, then you can analytically continue you might think, well, let's employ this device. Let's suppose that y is not a real number, as we supposed it was up to now, but y is an imaginary number, purely imaginary, and see if we can make sense of all the quantities in our theory in terms of this real number here and that imaginary number there. That would require that you analytically continue all your observations, observables, such as correlation functions. So you're saying your old correlation function used to be a function of x and y. So this is just like whatever it is, right? It's just some function of x and y. But under this substitution here, you're going to push this function of x and y outside of its domain of definition to apply in a wider setting of complex arguments, namely pure imaginary arguments there. And that process of extending the domain of definition of a function of several arguments to complex valued arguments is called analytic continuation. It's not always possible, but it turns out for the correlation functions of conformal field theory, it turns out to be in general possible that you can analytically continue these expressions. You just interpret x and y as actually being complex variables, and then you'll see that nothing really breaks and you can still interpret those functions now of these other arguments. So when you employ that device of analytically continuing your correlation functions, then it often happens, and I'm not sure under the exact conditions under which it's going to be generally true, but it often happens, at least I'll mention two words in a second, that these functions here will now yield a projective unitary representation of the conformal group of R1 plus 1. So it often happens that the endpoint functions, we call them Gn here, which were rotationally invariant and conformally invariant here, become invariant under the conformal group of R1 plus 1. This can happen. It's not a given that it will work. If you write out all the endpoint functions of your favorite conformally invariant quantum field theory in two dimensions, and then you try and analytically continue it, then it's not always going to be the case that you end up with a conformally invariant theory, a bunch of correlation functions which come effectively from a conformally invariant theory in 1 plus 1 dimensions. At least what might happen various things might happen upon this substitution of y equals it. Some of the things that might happen, for example, is that here you might have that the generator of translations is a positive operator and that you can talk about a ground state, but here you might lose that positivity. And other analytical horribilities might also happen. Now, I won't say anything more on this topic, except to mention reflection positivity as the criteria which would guarantee when this mapping will work. So reflection positivity is a condition that you can impose on these correlation functions to guarantee that when you do this analytical continuation, then many aspects will be preserved and we should end up with a nice Minkowski theory here. Now I want to stress again this little narrative just before we move on, because it becomes extremely tempting to do it the other way around. what we do is to obtain these quantum field theories that are invariant under the conformal group of Euclidean space, well, let's suppose we have one, then we're welcome to analytically continue the correlation functions in this way, and then we'll end up with a conformally invariant theory in Minkowski space as long as enough goodness happens and there's enough conditions satisfied. It's tempting to go the other way, and indeed you can, right? That's this reflection positivity is the argument here. And when you do so, it's very tempting to interpret certain equations on the Minkowski side in a physical way when you go to the Euclidean side. And I'll mention the final aspect of that here, which is that thermal states, sorry, time evolution becomes that one interprets time evolution as going to a temperature, a thermal state. And I'll just explain why people would say that, and then we'll get on to the business of building quantum field theories in Euclidean space. I'd recommend a book for a very, very clear explanation of all of this stuff at a very rigorous level. I'd certainly recommend the book of Glim and Jaffa. So if you have a nice Minkowski space quantum field theory, one that you've worked hard to build by canonical quantization or whatever, then one of the basic observables you might want to look at is this two-point correlation function, for example. Something you could imagine calculating in your favorite Minkowski theory. And because you worked very hard and you understand this theory very well, you know how to write that correlation function as, in the Heisenberg picture, the result of applying the time translation subgroup to this field here. Right? We suppose we have a sufficiently nice representation of the Poincare group, which has the translation group as a subgroup, that we can just write that operator like that in the Heisenberg picture. And now, if we want to make this analytical continuation to Euclidean space, right, we start saying, oh no, T, we have to undo this substitution here. So the way we undo that is T is minus I beta. Then, supposing this is allowed, you can interpret the result of that as e to the minus beta h hat phi hat x comma 0 e to the beta h hat phi at 0. Why am I doing these steps is the question?
Any of what you're doing right now. I'm not sure why. So you write the time evolution there, and then why are we doing this?
Why are we doing this? So what I said at the beginning, and I will remind you of this, is that we want to construct, whereas I've erased that thing, we want to build a quantum field theory with conformal symmetry. That will somehow correspond to this kind of data here. That means the observables, and since we're doing conformal symmetry in Euclidean space, so I didn't maybe emphasize that that's what we're going to be building today. We want to build these particular quantum field theories, ones that are invariant under the conformal group of R2, 0. Our observables will be labeled by space-time locations in Euclidean space. Now, so these quantum field theories are a little bit different to the ones that you're used to in relativistic quantum field theory. And they are so because they don't have as a subgroup the time translation group. So the group of conformal symmetries, or that's not quite the right way to say it. The group of conformal symmetries of R2O are dilations, translations, special conformal transformations, and rotations. This is a group that's completely different from the conformal group of Minkowski space R1, 1. That's a different group altogether. In this one, this preserves the light cone. This does not. We want to focus on building these kind of quantum field theories. What is this kind of quantum field theory? Well, it's a field theory with these kind of observables and which gives a projective unitary representation of that group. Now, it turns out that that's different to what we usually do. We have not as yet in your quantum field theory experience constructed such a quantum field theory that gives it representation of that. In the usual relativistic quantum field theory course, one constructs first a quantum field theory that is invariant under the Minkowski group. This is what we did in the quantum field theory course and the advanced quantum field theory course. Whenever you apply canonical quantization, you're not building such theories here, you're building these such theories. So the question is, how on earth are we going to build one of these things when so far we've only ever been building these things? Now, there's a neat trick called going to imaginary time that achieves exactly this goal. And this is what we're doing here. So our quantum theory yields a projective representation of blah. And supposing we had such a quantum field theory, then I'll argue that if you go to imaginary time and if enough things were true, then it would just correspond to a standard Minkowski field theory, and that you can also go the other way. So there's a way to build these theories by just substituting y is it, or t is minus I beta. And that is such a prevalent device that people don't often comment on it. They just say, we go to imaginary time, and it's one line in a presentation. However, there is much that's buried in that one line that I'm now here going through. And in particular, it's this point here that deserves some special mention. So if I want to use the correlation functions of a Minkowski quantum field theory to build a conformally invariant quantum field theory there, via this device of substituting t is minus I beta, then what does it mean quantumly? And I'm saying this in order to familiarize you with the language that people will use in many, many textbook presentations. And so when you take, for example, such a two-point correlation function from a Minkowski quantum field theory, you substitute t is minus I beta, then what happens is this, and that is essentially the correlation function for a thermal state of the Hamiltonian H. So this is ground state, e to the minus beta h. Essentially, but not quite, right? So we're almost done with this discussion. And this motivates the actual way we construct conformal field theories via the path integral. We look, instead of doing Minkowski, then analytically continuing, then writing out these correlation functions, what we'll do is we'll just say, let's suppose we have a quantum system at inverse temperature beta, write out the path integral for that theory, and then argue that theory exhibits a conformal symmetry under the conformal group of Euclidean space.
This is all unphysical because we have no time, right? Because
This is all completely physical. I don't. So the question was, this is unphysical because we don't have time.
R2, O is
R2, O is. So what is a quantum theory, right? A quantum theory is a Hilbert space and some collection of observables and a reference vector that we call the vacuum vector. Now, that's physical, or I've already, I don't know what interpretation of the word.
time evolution.
No, we don't need a time evolution. So we have to define what the word physical means, I think, before we go any further. A quantum theory is a physical theory. Let's start with maybe that as a definition. In the sense that maybe in principle there could exist a universe where that quantum theory is the one that governs its physics. Now, quantum theories don't necessarily have a time. Quantum theories as a kinematical theory of quantum theory is a Hilbert space and a collection of observables. Now, when your quantum theory corresponds to Euclidean space or Minkowski space or some other manifold, what that means is you have a unitary representation of the symmetries of that manifold on this theory. Sometimes you can find a subgroup that you say, hey, that's called time. But what does, maybe we should digress and talk about what does physical mean.
I thought it would be kind of useless if there was no time evolution.
So the comment was, you think it would be useless if there was no time evolution. I'd certainly argue strongly against that. I think we have every reason to think that the fundamental theory of nature doesn't have time evolution sort of baked in. And that could give you a trivial sort of reason why that wouldn't be, right? Presumably the universe is some kind of space-time foam down at the Planck level, and time and space are bubbling into emergence and spontaneously vacuum decaying. So there's every reason to at least leave open the possibility that there's not a God-given time axis on the quantum theory of the universe. So this is like one of the reasons why quantum gravity is so unbelievably difficult, because you can't bake time in beforehand. So let's start, let's digress and address the question. What does physical mean? For this course. So by physical, I'm taking a very broad view. I think you should have a Hilbert space. I think we're going to declare that the kinematics of a physical theory has a Hilbert space. I'm quite happy to live at that level of generality. You could go more general, right? As I mentioned in previous lectures, you could replace this with some cone of positive operators, positive linear functionals on some ordered unit vector space. You also want observables. You know, this is only kinematics, there's nothing happening here. This is just a place to describe states, but then you can't do any observations on them. So observables are a subset. I mean, they need not even be an algebra, and that's an important comment as well, right? So there's some kind of subset of the set of all linear operators on this Hilbert space. And it should be a Hermitian subset. You know, if you have some observable, then you should be able to take its dagger, and that should be in there as well, and that way you can make Hermitian observables. And there should presumably be an identity type observable. But beyond that, there's not actually many requirements that you need to make for this to already give you a fairly decent theory that has operational interpretation. So the Hilbert space here gives you the space of states, or more properly, the space of density operators. Or positive linear functionals. And these give you the observations. And so every experiment you can do is labeled, is some element of this set here, and everything gives you an expectation value, and that, or these label the POVM elements for the observables that you can do. Now, nowhere have I said time. Now, I argue that this is a perfectly legitimate theory. It even has an operational interpretation, right? We can attach experiments to the POVM elements in this set here. But I haven't said time yet. When does time appear in such a theory? Well, that's when we introduce dynamics. And dynamics is introduced in the following way, right? You take your favorite manifold, M, or set or geometry. I mean, I don't know, right? Even this is, in the case of quantum gravity, who knows what this thing is? Maybe this thing itself isn't well defined. But this is like one way to introduce dynamics. M, something, thing like a manifold. You build its isometry group. Presumably you can do that. You know, if the thing is well specified enough, then there must be some way to talk about distance maybe on that thing like a manifold. And you have the group of isometries of this manifold thing. And then you look for projective unitary representations on your Hilbert space H. And furthermore, at that moment, because you can now talk about doing this isometry or that isometry, you can start to try and attach labels to the observations as well. So introducing dynamics isn't just finding this group of unitary representations, but it's also about finding a set of observables here that correspond to points in this manifold-like thing. So there's a kind of intermediate step. Namely, you should find a way to label your observables by points in this thing, this manifold-like thing. Now, sometimes your manifold has a time direction. Sometimes it's just Minkowski space. And then, boom, we have dynamics, we have time. But sometimes your manifold could be the sphere, right? Why not take the sphere as a legitimate physical theory? You label all your observations by points on this sphere. Who knows? Maybe there exists sort of little bubbled-off universes which are spheres, where all the points in this universe are labeled by points on a normal two-dimensional sphere, and the group of symmetries of this sphere is no longer that of Minkowski space, but the group of isometries of the sphere, which is whatever, SO3. That universe doesn't have a time. I mean, it has one-dimensional subgroups which look a bit like time, but it doesn't have time. Similarly, in conformal field theory, we have theories where our observables are labeled by points not in Minkowski space, but in Euclidean space. And then there's no such thing as the right time, because because of rotation invariance. You know, if you choose one axis as time, the other axis is just legitimate axis to measure things with respect, and you can rotate from one to the other by one of these isometries. So there's no time in conformal quantum field theories in Euclidean space. And so that's what physical does not mean there exists a time in this course. It means something more general. Yeah?
I think the problem was, and I have a problem too with it, in our physical interpretation, we say we have a time when we make it imaginary, and this is somehow magically correlated to an inverse temperature. So we have these two observations or parameters, one time, one temperatures, and they are correlated.
Yes.
That's not the first guess I would take.
No. Okay. Yeah.
Undergraduates.
So to paraphrase, we have these conformally invariant theories. We have Minkowski theories, and then by this magical substitution here, somehow time has something to do with temperature, and it's not a priori obvious why, how, when. I agree. That's a very non-obvious part of this story.
Physical interpretation.
But it turns out, you know, that physicists have got a lot of practice with this trick, and they understand the intuition very well now, that you can draw this analogy make this analogy quite concrete. And I'm not going to explain sort of like why this works, because I don't think I'm pretty sure I don't understand why this works. But it is an analogy, it is exploited often, and it's how we build a great class of conformal field theories are built precisely by studying thermal studying quantum systems at inverse temperature beta. And roughly speaking, the way that works, why this should work, is because the group of isometries of Euclidean space with an imaginary time get transformed into the group of isometries of Minkowski space. You've seen this, I think, in special relativity. If you do a Lorentz transformation and you change the rapidity parameter to an imaginary number, you get a rotation. So that's sort of the naive answer. It just it works because you just sines go to sinches and causes go to coches. I mean, in some sense, that's exactly the answer. Okay, so this is a confusing point. I mean, even amongst the best textbooks, this point, I think, deserves more attention, and unfortunately, it's not explained sufficiently in many, many places I know.
So, you could say in a way that time is more like an emergent phenomenon, in a way that you made out as, in this case, the time translation group is a subgroup, but it may not happen.
Yeah, so in this, to paraphrase, time is like an emergent phenomenon here. Sometimes you notice that your theory has a one-dimensional subgroup that behaves like time in Minkowski space, and sometimes not. And although it's baked into the axioms of quantum mechanics in textbooks that you have time in the Schrödinger equation, that's actually, I'd argue that that's too many axioms for quantum. Right? It's sufficient to have quantum theory with kinematics observables, labeled observables perhaps, and dynamics, but the minute you go the step further and demand that your dynamics are that of Minkowski space or non-relativistic Galilean space, you've gone a step too far, right? You've added just that too many axioms.
Time entropy is the choice of M, right?
Time is the choice of M, yeah, if you like, yeah, exactly that there. So, how can I do quantum mechanics without the Schrödinger equation? Well, you are. As soon as you do the unitary representation of a symmetry group, you're doing the Schrödinger equation. But you need not have baked the Schrödinger equation in to the axioms. Just like projective measurements, I would argue, are a completely superfluous additional axiom in quantum mechanics. We don't need projective measurements to talk operationally about quantum theory. And indeed, I've yet to have anyone explain to me an experiment where a projective measurement actually took place. All right, where are we? Well, we're still on page 1 of my notes. So, but this was an interesting and important digression, I think. Now, the rest is just a somewhat straightforward bunch of changes of variables. And that's what's going to sort of occupy us, is the mechanics of changing variables from now on. So at the moment, we're labeling our observables by space-time locations x, y. We're looking at Euclidean CFT. So our space-time that our quantum theory corresponds to is just R2 with these coordinates here. Oh, I've used x and y, but here we go. It's just going to be lists of changes of variables. x0, x1. Sigma 0, sigma 1. So now we're going to do a lot of things for the sake of convenience. Ah, drat. Okay. Damn it. Sorry about this. Our next goal is to interpret various operations we're going to do on our field theory. And to aid in the interpretation, we're going to try and do this imaginary time substitution and keep track of what each operation means under these changes of variables. So Minkowski quantum field theories have a light cone, etc. So our first step to building a conformal quantum field theory in Euclidean space is to make this imaginary time substitution. So we start with our Minkowski conformal field theory, and then we replace this sigma 1 variable by I times sigma 1. And we define new complex variables zeta well, I guess I'll use x, z. Sorry. So we're going to define new coordinate z, which is sigma naught plus I sigma 1. And we're going to label all our correlation functions and observables instead of using sigma naught and sigma 1 by z and z bar. This is this analytic continuation step. So this theory here, we have our Minkowski conformal field theory. All its correlation functions are labeled by points in Minkowski space. These are just sigmas, these vectors of sigmas here. And we analytically continue these correlation functions here to depend now on z's and z bars instead of sigmas and sigma naughts and sigma ones. So this is this is the Euclideanizing step, the imaginary time step is sometimes referred to. The next step is just going to be changes of variables. So this first step here is the Euclideanizing step. We are labeling space-time locations now instead of by points in a Minkowski space, by points in a Euclidean space. And we've complexized the coordinates as well. So instead of saying x comma y, we say z, and z means the complex combination sigma naught plus I sigma 1. Now, we take a seemingly dramatic step. We're going to completely change our manifold from that of R2 to that of a cylinder. So we don't no longer look at space-time Euclidean space. We instead compactify the space direction or time direction, whatever you like. They're the same in Euclidean by saying that sigma 1, for example, equals sigma 1 plus 2 pi. Now, why do we do this? Well, it gets rid of, this is like undoing the thermodynamic limit. It gets rid of infrared problems. Some infrared problems go away. So there's divergences that you get when you have an infinite system. And also you can think of this as really being, corresponds to a say it corresponds to a system on a circle with radius r, and you let radius go to infinity afterwards. It's a device. It's a useful device. So it's useful to compactify space at this point. So previously we had our conformal field theory on Euclidean space. Now we have our conformal field theory on a cylinder. And at the same time, it's convenient to define new coordinates You know, we could always label our cylinder coordinates just by where they are on the circle and where they are on along the cylinder. But we're going to define new coordinates by taking the exponential of our old z coordinates. So when you do this, the point down here at minus infinity, sigma naught is minus infinity, maps to the origin of this new coordinate system here. And the point at sigma naught equals infinity maps to infinity on this representation here. So we're not going to use those coordinates after all. We're going to use the exponentials of those coordinates to label positions in our cylinder system. Defines, equal sign with triangle is define, or redefine. I can change the notation, perhaps. Maybe you're more comfortable with this. So, all these, when we now refer to a point in this manifold here, which is none other than the complex numbers, then each point here has a corresponding point on this cylinder here, this system with a space direction, which is compactified in a time direction, which goes forever. And this is where we're going to build our quantum theories. We're going to build our quantum theories here on C, and then we're going to interpret every observable here as corresponding to something on this compactified space-time over there. So there's some operations you can do. Oh yeah, firstly, if you have a constant time on your compactified space, that corresponds to a circle in C. And time inversion corresponds to Z gets maps to 1 on Z complex conjugate. Time translation in the cylinder universe corresponds to, under this change of variables, to dilation. And usual translation translates to rotations. So the coordinate system that we're going to use has the following interpretation. A point in this complex plane corresponds to, we've done this analytic continuation of replacing time with imaginary time, corresponds to a point on a cylinder space-time where you are along the cylinder depends on the radius of your point in complex space, and where you are around the cylinder depends on your angle. Now this is all sort of window dressing for the theory we're going to construct. So we're now going to construct and we're doing all of this because we want to use path integrals for thermal states to build our conformal field theories. And that means we want to interpret various symmetry group actions as having some counterpart on a Minkowski spacetime. And it turns out under this particular choice of coordinates, when we do a certain symmetry operation on this C here, that would have a counterpart on Minkowski spacetime, but not Minkowski spacetime, but Minkowski cylinders, where you've compactified space. And this is very useful when we want to interpret, for example, time. As it happens, time is the one generator that we really do want to understand, and we're going to get to that. Yeah, I wonder what's the right order to do this in. So we'll do it this way. I'm going to show you a magical technique for taking a conformally invariant classical theory and producing a bunch of operators which obey the right symmetry algebra to give you a conformal invariant quantum theory. It's a very beautiful and magical technique. And how this works is that you get your conserved charges corresponding to some symmetries. And put hats on them. Right? That's roughly speaking how it's going to work. So if you have some this is classical, right? If you have some conserved charges for some symmetries in a classical system, then they have their Poisson brackets closed to give some kind of algebra like this. And inverse Noether's theorem gives you these charges, and inverse Noether's theorem shows you that these generate all the symmetries. Now, to quantize, you just put the hats on, yeah? Great, that was easy. But now you've got two problems. So it looks like this is a solution to the quantization problem. You have some classical theory, you just put the hats on, and now you have a quantum theory, and that's fine. But this is an abstract written down thing here. There's no Hilbert space here, and there's certainly no interpretation of these operators in terms of a field. Apart from inspired guessing, I don't know how to actually... There's no H. There's no Q equals some function of fields. There's a lot of work to do, right? Putting on hats isn't just putting on hats. And you're not given much guidance here of how to actually find the correct Hilbert space and so on. That's what canonical quantization is, right? It's a way of putting on hats and dealing with all these sub-problems here and dealing with it in a consistent way. But you're often given not very much guidance on how to express the conserved charges as functions of the fields. You know, because of operator ordering ambiguities, this is not clear. You're not given much guidance on H. The way you deal with that in canonical quantization is you work out what the positive frequency components are and the negative frequency components are. You find your harmonic oscillators and you look for harmonic oscillator representations. But that works well for free fields. But as soon as we get to more complicated fields, you lose rapidly the guidance you need to solve these problems. But there is one technique which gives you, works surprisingly often and gives you all the guidance you need, and that's the path integral. So path integral quantization is a fantastic heuristic for building quantum theories, which you can then a posteriori go ahead and check are legitimate quantum theories. So it's a guessing box, very useful one. You put some data in and it will hand you back some data, and then you'll check, is this data a good quantum theory? And it works so well, so often, that you gain good intuition when it's going to work, that you don't really ever bother constructing things canonically and correctly. So I'm going to show you a neat derivation of how to get the generators, the quantum generators corresponding to classical symmetries. This is called a Ward identity. So we start off with some classical field theory with some action. Phi is a vector of fields, so we're not dealing with just Klein-Gordon fields here, we can have all kinds of stuff. And I'm going to assume that S has some symmetries, right? And conformal symmetry is the symmetry that's the most important for us. And such symmetries always have this kind of form. So in infinitesimal we have infinitesimal form of the symmetry. So we have our action, it's invariant under these transformations here. So to explain the notation. So this space-time label is the same everywhere. So omega are a list of infinitesimal parameters, and G act on the vector label of phi. So what we're really saying is that phi prime of x is the exponential of minus I omega A G A. No hat. So all Lie groups have this structure, right? So all compact Lie groups. So our action is invariant under these infinitesimal symmetries there. And what does it mean for a classical theory to be invariant under a group of symmetries? Well, it means that the action is invariant up to a total derivative. Oh, sorry, the Lagrange density is invariant up to a total derivative. Now we're going to use the path integral prescription to see what one of these symmetry operations does on the expectation values, on correlation functions. So now we're going to talk about quantum theories. So, as you no doubt remember, hat, the correlation function for a bunch of quantum fields has the following expression as a path integral. Right? That's the formula that you're required to remember in the path integral prescription. Let's do one of these symmetry transformations over here on the path integral side. See what happens. And we'll learn quite something interesting, actually. We're going to do some variable changes, and we're going to see what's the result of referring not to phi, but the result of doing a symmetry transformation on phi. So instead of doing everything with respect to the variables phi at x, we're going to do everything with respect to phi prime of x, where phi prime is the symmetry transformed field up here. It's just a change of variables so far. And we're going to make a big assumption, this is a big one, that the integration measure is invariant. Now when that isn't the case, you get things called anomalies. So it's an assumption at this point. I mean, it's often easy to verify that it's true, but it's not always true. It's not a given that even under the most innocuous looking symmetries that this measure is invariant. But let's suppose that it is. Then what happens to this nice correlation function here, which I'll just call x, big X hat, is the following, right? Nothing. If the measure is invariant under that change of variables there, then what you get, I'll drop the limit from now on. Everyone knows that limit's in there. Phi prime, right? I'm changing the variables, and then I've got to express each of those phi's in there in terms of phi primes, which means I have to undo this symmetry over there, so I add it on. I'm just going to write that as d of x, or x plus d of x. I'll explain what that means in a second, but I hope it's kind of clear. Exponential. And the action changes as well, right? The action's not totally invariant. Well, it is invariant unless I do something tricky, and I'm going to do something tricky. And there's the path integral there on the bottom as well. So I'll explain what's just happened there. Okay, we've done a more general change of variables than I otherwise implied. So the actual change of variables is phi prime of x equals phi of x minus I omega a g a omega x. So the actual change of variables that we can do, if we want to, is we can allow these infinitesimal parameters to depend on x. And when you do that, then the action is no longer invariant under this change of variables. I mean, the measure is still invariant, but the action isn't. And if you recall, this is how you prove Noether's theorem, right? The way to prove Noether's theorem is one tricky way is to allow your symmetry transformations to depend on space-time, and then you get a conserved current. And that's precisely this J A mu here. That's the conserved current corresponding to the symmetry transformation. Phi prime equals phi minus I omega A G A. So this isn't just mechanics. You can just go ahead and check that that's how your action changes. And I promised I'd explain what x plus dx means. Right? The way x stands for the product of all the fields, x1 through to xn. And x, therefore, plus dx is, well, that plus first order shifts. As n terms. Now let's just note the obvious, right? That the left-hand side equals the right-hand side. So to order 1, the terms match. This is a common trick, right? You transform, use the fact that the left-hand side equals the right-hand side. The order 1 terms are the same and unchanged and therefore match. But order omega terms lead to a non-trivial conclusion. So order omega a x leads to the following expression. And this is an exercise. So this is an exercise to derive that. So it's really only a matter of just looking at this term here that I wrote out already, expanding this right-hand side to order omega. There's an omega here, so there's a first order term there, and there's also a first order term here, and making sure that everything vanishes to order omega. And then you learn this fantastic result here. So if you were to go the canonical quantization route, if you had some symmetries and you worked out the conserved charges and the algebra they obey and everything, if you want to go the canonical quantization route, then you're in for trouble. You have to work really hard to find the harmonic oscillator representation. Then you have to find what are the appropriate quantized version of these charges here in terms of the quantum fields and so on. You have to work hard. It's not impossible, you just have to work hard. On the path integral side here, it immediately tells you what the generators are of the symmetries, if you look at this expression here. So phi hat is phi hat, it's the quantum field itself. G hat is just a matrix that acts on the vector valued quantities here that you find just by using the old G there. So G is G, there's nothing that changes there. And J hat of mu, of A, that's some expression in terms of the classical fields, but then you stick it in the path integral, and that's the equivalent of putting a hat on the fields inside that current there. So this is where this operation here is defined. This is defined by, if you just look at this expression here, J hat is that operator that results from this expression here in a path integral. So if you like, that's the definition of J hat. So the generator of the symmetry is handed to you already just by the path integral prescription in terms of the field. So J is some function of the phis. And we'll go through the explicit J's in the next lecture for conformal symmetry. So when we have dilation, for example, this J hat here is the energy momentum tensor times by X. If you have translations, J is just the energy momentum tensor. If you have rotations, then J is the energy momentum tensor multiplied by the rotation. No, that can't be right. But certainly for dilations and translations, rotations are energy momentum tensor times epsilon. Yeah, we'll get to that. So you'll be able to work out what the classical J is, and then via this path integral prescription, you'll instantly be able to put hats on to find out what the quantum currents are that correspond to these symmetries, without having to go through all this painful route of canonically quantizing. So that's where this method is very useful, and this is called a Ward identity. Okay, I think we'll stop there. Thank you very much.